Welcome back, deep divers.
Mm.
Today, we're going to jump headfirst into the world of medical AI.
Oh, yeah.
But not just any AI.
Right.
We're talking about a totally new approach to training AI models.
Mm-hmm.
To not just, look at your medical images,
Yeah.
but to really understand what they're seeing.
Wow.
Imagine an AI that can, point out the exact spot
Uh-huh.
on your X-ray that might be concerning.
Oh, wow.
And tell your doctor why it's worried.
Interesting.
That's the kind of potential we're diving into today.
That's a huge leap forward from the AI we've seen before up
Right.
to now.
Hmm.
Medical AI has been good at recognizing patterns in images. Say, knowing that a chest X-ray looks like pneumonia,
Okay.
but not so great at pinpointing the precise location of the problem.
So it's not enough for the AI to just give a general diagnosis.
Right.
It needs to be able to say, hey, doc, look right here.
Yeah.
This is the spot you need to focus on.
Mm-hmm.
Why is that precise location so important?
Think about it this way. If your doctor just knew you might have pneumonia,
Yeah.
but didn't know exactly where the infection was,
Right.
how could they treat it effectively?
That's a great point.
That precise localization is crucial
Yeah.
for making treatment decisions
Makes sense.
and also for building trust in AI diagnosis.
For sure.
Doctors need to be confident that the AI is pointing them in the right direction.
Absolutely. Okay, so how does this new research address this limitation?
Well, this is where it gets really interesting.
Right.
The research we're looking at today
Mm-hmm.
introduces a new AI model called UMed-LVLM,
Okay.
which stands for Unveiling Medical Abnormalities.
Unveiling Medical Abnormalities, UMed-LVLM.
And you know what?
What?
That name is spot on.
Okay.
This AI is trained to do exactly that.
Uh-huh.
Unveil those subtle abnormalities in medical images.
Cool.
That might be easy to miss.
I like it.
Yeah.
It's catchy and it tells you exactly what it does.
All right.
But what makes this particular AI so special?
It's all about the way UMed-LVLM learns.
Okay.
The researchers have developed a two-stage training process
Okay.
that's pretty groundbreaking.
Got it.
The first stage is all about teaching the AI
Yeah.
to understand medical language
Uh-huh.
in the context of images.
Okay.
It's like giving the AI a medical vocabulary lesson.
So instead of flashcards?
Yeah, but with pictures instead of flashcards.
Got it.
So it learns that the phrase pulmonary nodule
Yeah.
refers to a specific kind of spot
Mm-hmm.
on a lung X-ray, for example.
So the AI is learning to speak doctor,
Right.
connecting words to actual visual cues.
Exactly.
Okay, got it. What about the second stage of training?
This is where it gets really cool.
Ooh,
They call it abnormal aware rewarding.
interesting.
And it's kind of like training a dog with treats.
With treats, okay.
Every time the AI correctly identifies the location
Yeah.
of an abnormality in an image,
Mm-hmm.
it gets a reward.
So the AI is learning by getting positive reinforcement,
Yeah.
just like we do.
Exactly. But what kind of reward are we talking about here? Does it get a virtual pat on the head?
Maybe not a pat on the head,
Okay.
but the concept is similar.
Okay.
There are actually two types of rewards
Okay.
working together
Just
to help the AI learn.
got it.
The first one is called the abnormal localization reward.
Abnormal localization reward.
As the AI gets closer and closer to drawing a box
Uh-huh.
around the exact abnormality, like a doctor would circle something suspicious
Okay.
on an X-ray,
I see.
the bigger the reward it receives.
So it's being trained to be incredibly precise,
Right.
to zero in on the problem area with laser focus.
Exactly.
I bet that takes a lot of practice.
It does.
What's the second type of reward?
The second reward is called the vision relevance reward.
Vision relevance reward.
And this one is all about encouraging the AI
Okay.
to pay attention to the visual cues
Yeah.
that indicate an
I
abnormality.
got it. Yep.
It's not just about finding the right location.
It's about understanding why that location is suspicious.
That's fascinating.
Yeah.
So it's learning to analyze the image like a human doctor would,
Mm-hmm.
looking for those subtle signs that something might be wrong.
Right.
It's not just memorizing patterns.
Right.
It's developing a deeper understanding of what it's seeing.
You got it.
That's incredible.
And that's a major difference from
Yeah.
previous medical AI models.
Right.
This dual reward system
Yeah.
is actually mimicking how human doctors learn
Wow.
by connecting visual patterns with medical knowledge.
That's a huge step forward.
Yeah.
So it's not just about brute force memorization.
Right.
It's about building genuine understanding.
Exactly.
Now, I'm curious, what kind of medical images
Oh, yeah.
did they use to train this AI?
Good question.
Was it just X-rays, or
Yeah.
did they use other types of images as well?
They went all out.
Okay.
They trained UMed-LVLM
Yeah.
on a really diverse set of medical images.
Okay.
X-ray,
Yeah.
CT scans, even endoscopic images
Right.
from inside the digestive system.
Wow, they really covered their bases.
Yeah, they did.
So they weren't just trying to teach it about one specific disease or organ.
Mm.
They wanted to build adaptable diagnostic skills
Exactly.
that could be used across different areas of medicine.
That's the goal.
That's incredible.
And you know what?
Like-
It worked.
Really?
The results were pretty impressive.
Yeah.
UMed-LVLM actually outperformed
Interesting.
other state-of-the-art AIs
Wow.
in accurately identifying and describing abnormalities
Amazing.
across all those different image types.
That's really cool.
Yeah.
I'm really curious to hear about some specific examples
Uh-huh.
where this AI really shined.
Sure.
Were there cases where it was able to spot things
Oh, yeah.
that other AIs or even human doctors might have missed?
Oh, absolutely.
Give us an example.
There were several cases
Right.
where UMed-LVLM was able to correctly identify and locate abnormalities that even some of the most powerful general-purpose AIs,
Okay.
like GPT-4V,
Yeah.
struggled with.
Interesting.
For instance, there was one case with a chest X-ray
Okay.
where UMed-LVLM was able to pinpoint a very subtle lesion
Mm-hmm.
that suggested pulmonary tuberculosis.
Okay.
GPT-4V didn't even attempt to localize it.
So it's showing real potential in areas
Yeah.
where even some of the most advanced AIs are still lagging behind.
Right.
So incredibly exciting.
I know. It's pretty cool.
But I'm also curious about the details.
Okay.
The nuts and bolts
Yeah.
of how they trained this AI and what kind of data they used.
Well, that's a great place to pick up
Okay.
in the next part of our deep dive.
Right?
We'll delve into the nitty-gritty of the MAU dataset.
Ooh, the MAU dataset.
That's a collection of medical images they use for training.
Okay.
And we'll explore some of the clever techniques they use to make sure the AI could learn from such a diverse range of images.
Sounds good. I'm ready to get into the details.
Okay.
Let's do it.
Okay, so you're curious about the data they fed this AI.
Yeah, like if you think about it, it's not like every X-ray or CT scan comes with a handy little label saying an abnormality right here.
Exactly.
So where did they find all this data?
Well, they did an amazing job of pulling together information
Okay.
from different sources to build what they call the MAU dataset,
Okay.
which stands for Medical Abnormalities Unveiling.
MAU dataset, medical abnormalities unveiling.
Yeah, another catchy name.
I like it.
So what exactly went into this MAU dataset?
Yeah, was it all just different types of X-rays?
Actually, they used a really interesting mix of imaging types,
Okay.
which helps ensure the AI is ready to handle all sorts of medical scenarios.
Yeah, makes sense.
They used several sets of CT scans,
Oh.
which give very detailed 3D images of the body.
Mm-hmm.
For example, they used deep lesion,
Deeply.
a data set containing axial CT scans,
Okay.
which are kind of like slices through the body.
I see.
These scans show different abnormalities.
It's like lesions,
Lesions.
which are basically areas of damage or irregular tissue
Okay.
in places like the lungs, abdomen, and liver.
So that's covering a pretty wide range of potential problems already.
Right.
Wow.
And they didn't stop there.
Okay.
They also included data from the kidney stone dataset,
Kidney stone dataset.
which focuses on,
Okay.
you guessed it,
Right. Kidney stones.
kidney stones.
Okay. They used renal CT scans,
Mm-hmm.
which are specifically for the kidneys.
Okay.
And these showed kidney stones in all different sizes and locations.
So we've got lesions, kidney stones, any other types of images in the mix.
Oh, yeah.
Okay.
They broadened the scope
Okay.
to include chest x-rays from the NIH dataset.
NIH dataset.
This one is really interesting because it covers lots of different conditions you hear about all the time.
Oh,
Things like
yes.
pneumonia and tuberculosis.
So things that everyday doctors are dealing with all the time.
Exactly. And to
Okay.
make sure they had a really good understanding of tuberculosis in particular,
Mm-hmm.
they also use the TBX11K dataset,
TBX11K dataset.
which is specifically for detecting tuberculosis from chest x-rays.
So they really zeroed in on respiratory conditions,
You did.
which are obviously a huge concern in medicine.
Right, but they wanted to go even further
Okay.
beyond just lungs and kidneys
Okay.
to round things out.
Mm-hmm.
They included endoscopic images from the KVS-SIRE dataset.
Endoscopic images. That sounds intense.
Yeah.
What are those exactly?
These are pictures taken using a tiny camera
Okay.
that's inserted into the body,
Yeah.
usually through a natural opening.
Got it.
The KVASR dataset
Yeah.
specifically includes images of the gastrointestinal tract.
Okay.
So think esophagus, stomach, intestines.
Okay.
These images show things like polyps,
Polyps?
which are small growths,
Okay.
and even tumors.
Wow. So we're talking about a really wide range of imaging modalities
We are.
and medical specialties represented in this data set.
Yeah.
That must have been a lot for the AI to process.
It was.
How did they make sure it could actually learn
Right.
from such a diverse collection?
That's where their clever prompt method comes in.
Okay.
They actually used another powerful AI called GPT-4V
GPT-4V.
to help generate detailed descriptions of the abnormalities
Interesting.
in each image.
So it's like they had one AI teaching another AI.
In a way, yes.
That's so cool.
GPT-4V was given information about the type of abnormality and its location in the image, and then it generated a diagnostic description, including details about the bounding box or the area that needs to be focused on.
So they were training UMed-LVLM not just to find the abnormalities,
Right.
but to describe them in a way that doctors would find useful and understand.
Exactly.
Wow, that's really smart.
And of course, to be extra safe
Yeah.
and make sure those descriptions were accurate, they had medical experts double-check all the information
Makes sense.
that GPT-4V generated.
That's reassuring.
Yeah.
It's good to know that human expertise is still essential in this process.
Absolutely.
So just to recap, they combined this super diverse MAU data set
Yeah.
with a clever AI-assisted prompt method
Right.
to train UMed-LVLM to both see and understand medical abnormalities.
That's right.
Pretty impressive stuff.
It is.
But did the researchers run into any snags along the way?
Yeah, they did mention a couple of key limitations.
Okay, like what?
The first one is something that a lot of medical AI researchers are grappling with.
Okay.
The availability of annotated data.
Annotated data, yeah.
Meaning medical images that have been carefully labeled with information about what's in them, right?
I imagine it's not easy to find huge data sets of medical images that are already labeled in a way that's useful for AI training.
Exactly.
Yeah.
Medical data is incredibly sensitive.
Right.
And there are strict regulations about privacy and access.
Okay.
On top of that, you need trained medical professionals to go through all those images and label them accurately.
Right. Which takes a lot of time and resources.
Yeah, it does.
So even though they put together this amazing MAU data set,
Right.
they were still limited by how much readily available labeled data was out there.
Exactly. The researchers acknowledged that if they had access to even more data, even more diverse examples, they could probably boost UMed-LVLM's performance even further.
That makes sense.
It's like anything in life.
Yeah.
The more experience you get,
Right.
the better you become.
For sure.
And that goes for AI too.
Makes sense. So what was the second limitation they mentioned?
The second limitation has to do with computational resources.
Okay.
Training these large, complex AI models
Yep.
takes an incredible amount of computing power.
I can imagine.
Even with access to powerful computers,
Right.
the training process can take a really long time.
So they were basically limited by the available technology,
That's right.
which might have restricted the size and complexity of the AI they could create.
Exactly.
Wow.
And it really highlights the need for more powerful computing technology
Yeah.
to keep pace with all the incredible AI research that's going on right now.
It's a good reminder that we're still in the early stages of AI development.
We are.
There's so much potential,
Huge potential.
but there are still hurdles to overcome.
Absolutely.
It's really interesting to think about.
It is.
Even with those limitations, the researchers were able to make incredible progress with UMed-LVLM.
Absolutely. They did a great job.
And it sounds like they didn't stop at just training the AI and seeing how it performed on the MAU data set.
Yeah.
They also wanted to understand how different factors influence the training process and what this research could mean for the future of medical AI in general.
You're absolutely right.
Okay, so what did they learn?
And they uncovered some really fascinating insights along the way.
Okay, give us some examples.
For example, they looked closely at the impact of precise localization on the AI's diagnostic performance.
Okay, let's dig into that.
Okay.
What did they discover about the importance of being super accurate with pinpointing those abnormalities?
Well, what they found was that even tiny improvements in localization accuracy led to significant improvements in how well the AI could diagnose a problem.
So the more precisely the AI could say, the problem is right here,
Exactly.
the more likely it was to give a correct diagnosis.
That's what they found.
That makes intuitive sense.
It does.
But interestingly, they found that the benefits seemed to level off.
Yeah.
After a certain point.
Right.
So beyond a certain level of accuracy, making the localization even more precise didn't seem to make a huge difference.
That's right.
That's really interesting.
It is.
It suggests that there's a sweet spot for localization.
Yeah.
A point where getting any more precise might not be worth the extra effort. That's valuable information for researchers who are working on similar AI models.
For sure.
I like that.
And they also made a key discovery about the amount of data they used for training. They found that the more data they fed the AI, the better it became at understanding and describing abnormalities and following instructions.
So basically, the AI learns best when it has lots and lots of examples to work with.
That's right.
Kind of like how we learn best.
Yeah.
Through experience and exposure to different situations.
Exactly.
That's really cool.
It emphasizes how crucial it is to build large and diverse data sets for medical AI. The more examples the AI sees, the better it becomes at recognizing patterns and making accurate judgment.
It all makes perfect sense.
It does.
But I'm curious.
Yeah.
Did they just test UMed-LVLM on the same data sets it was trained on?
So, good question.
Or did they try to see how well it could generalize to new, unseen medical images?
They did. They wanted to make sure UMed-LVLM could apply what it learned to new situations, which is a real test of intelligence.
Absolutely. I'm eager to hear how it performed.
Okay.
Did it pass the test?
Well, they tested its generalization ability in a few different ways. First, they tried something called leave one out training.
Leave one out training.
They'd remove an entire category of images, say all the chest x-rays, during training. Then they'd see how well UMed-LVLM could diagnose problems in those chest x-rays, even though it had never seen them before.
So basically they were testing if the AI could apply knowledge from one area to another, even if it hadn't been specifically trained on that area.
Precisely.
Cool.
And while its performance was a bit lower than when it had been trained on those images, UMed-LVLM still showed a real knack for generalizing.
Interesting.
That tells us it wasn't just memorizing patterns, it was actually learning underlying concepts.
That could be applied to new situations.
That's encouraging. It means this AI has the potential to be adaptable and useful. In a whole range of medical settings.
It does.
Not just the very specific ones it was trained on.
That's the goal.
That's great.
They also took it a step further. And tested UMed-LVLM's ability to generalize across different medical data sets entirely. They'd train it on one data set and then evaluate its performance on a completely different one.
Wow.
With images it had never encountered before.
So it's like taking an AI that's learned from CT scans. And then seeing if it can interpret X-ray images or endoscopic images. That's a real challenge.
It is. And again, UMed-LVLM outshone other models in its ability to generalize.
That's awesome.
This suggests that it really could be a valuable tool in real-world medical settings where doctors are constantly dealing with diverse imaging techniques.
Makes sense.
That's truly remarkable.
It is.
So this AI is showing incredible promise.
It is.
In terms of accuracy, pinpoint localization, and even generalization to new situations. What else did the researchers discover?
Well, they also explored how UMed-LVLM handled different types of imaging modalities. They trained it on images from just one type, like CT scans. And then tested it on a different type, like X-rays.
So like teaching the AI one visual language. And then seeing if it could translate that knowledge to a different visual language.
That's a great way to put it.
Did it work?
It did.
Wow.
They found that UMed-LVLM was significantly better at this cross-modal generalization.
Cross-modal generalization.
Than on other models.
That's amazing.
Yeah.
It's like they figured out how to teach AI to be multilingual. But with medical images, instead of spoken languages.
That's a great analogy.
And it's this ability to adapt and generalize
Right.
that makes UMed-LVLM so exciting. It hints at a future where AI can help doctors in all sorts of medical settings.
Exactly.
Regardless of the specific imaging techniques or medical specialties involved.
Right.
This is all incredibly promising.
It is.
And I'm sure our listeners are as fascinated as I am.
I hope so.
But I'm also thinking about the bigger picture here.
Okay.
What are the implications of this research?
Right.
How could it change the way we approach medical diagnoses in the future?
That's a great question. The researchers believe that UMed-LVLM could help doctors make more accurate diagnoses earlier.
Okay.
Personalized treatment plans based on what the AI sees in the images, and even discover new diagnostic markers that might be too subtle for humans to notice.
It's like we're on the verge of a whole new era of healthcare.
I think so.
Where AI and human expertise work together to improve patient care in ways we can only begin to imagine.
It's a future filled with exciting possibilities.
It really is.
Yeah.
It really does feel like we're on the cusp of something amazing.
You
know?
Yeah.
When you think about AI's potential to transform healthcare, but like with any powerful new tool,
Right.
we have to make sure we're using it responsibly right.
Oh, absolutely.
I mean, what are some of the things we need to be thinking about?
Yeah, that's a great point.
As AI becomes more common in medical settings.
You've hit on a really crucial point.
Yeah.
As we develop these increasingly sophisticated AI tools, we have to be incredibly careful about how they're used.
Right.
And make sure they're benefiting all patients equally.
It would be a real shame if this amazing technology ended up creating new inequalities in healthcare.
Yeah.
Or making existing ones worse.
Exactly.
Yeah.
We have to make sure these AI models aren't picking up biases from the data they're trained on.
Right.
Because that could lead to inaccurate or unfair diagnoses for certain groups of people.
That's a good point. So it's not enough to just focus on the technical aspects of AI development. We also need to be thinking about the social and ethical implications.
Absolutely.
Yeah.
And that means having diverse teams of people involved in developing and testing these technologies. Doctors from different specialties, data scientists, ethicists, and of course, patients themselves.
Of course.
Everyone needs to have a seat at the table to make sure these tools are designed and used in a way that's fair and equitable for all.
I think it's also important to remember that AI is a tool, not a replacement for human doctors.
Couldn't agree more.
Yeah.
Ultimately, it's the doctor who's responsible for making the diagnosis and deciding on the best course of treatment. AI can provide incredible insights and assist doctors in making those decisions, but it shouldn't be making those decisions on its own.
It's all about finding the right balance.
Yes.
Harnessing the power of AI while still keeping human expertise at the center of patient care.
Exactly.
And as these AI tools become more integrated into healthcare systems, we need to think carefully about transparency.
Absolutely.
Patients have a right to understand
they do.
how AI is being used in their own care. And doctors need to be able to explain the reasoning behind AI-driven recommendations.
It's about building trust. Making sure patients feel informed and empowered in their healthcare journey.
Exactly.
Open communication and clear explanations are essential.
Totally.
And as we move forward, we need to keep having open and honest conversations about the ethical and societal implications of AI in healthcare.
This isn't just a discussion for scientists and tech experts.
No, it's not.
It's something we all need to be thinking about and talking about as a society.
I wholeheartedly agree. As AI becomes more and more intertwined with our lives, and especially with something as important as our health, we all have a responsibility to shape its development and make sure it's used in a way that benefits humanity as a whole.
It's a call to action for all of us.
It is.
To engage with this technology thoughtfully and responsibly.
Absolutely.
So as we wrap up this deep dive into the world of medical AI, what's the key takeaway you'd like our listeners to walk away with?
I think the most important thing to remember is that AI has the potential to revolutionize healthcare for the better. But it's up to all of us to make sure that happens.
That's a powerful message.
It is. It's really important.
We need to approach AI development with a sense of both excitement and caution, recognizing its potential.
Yeah.
While also being mindful of the potential pitfalls.
Absolutely.
It's a balancing act.
It is.
But it's one that we have to get right.
We do.
Well said.
The future of healthcare is being written right now.
Yeah.
And AI will undoubtedly play a major role, but it's a future we must shape together.
And on that note,
yes,
we'll wrap up another deep dive.
Great.
We hope you found this exploration of medical AI as fascinating as we did.
It's really cool stuff.
Until next time, keep those minds curious.
Yeah.
And don't be afraid to ask the big questions.
Ask those questions.